Good afternoon, everyone. My name is Dev Agarwal, a third year BTech student from VIT Chennai, and today I'm going to present a research titled Optimization Algorithm for Wheat Harvest Classification, a Hybrid Computational Approach. So, let's start with why quantum computing in agriculture. So, basically precision agriculture relies on timely and accurate classification of crop development stages to optimize harvest timing and maximum yield. These projects represent a hybrid computational approach where we have successfully combined the reliability of classical deep learning with emerging power of quantum computing to solve critical problem in precision agriculture. Wheat is globally critical crop, and for farmers, timing is everything. Determining the exact harvest stage is essential for maximizing yield and ensuring grain quality. Currently, this process is mostly manual. It is subjective, time consuming, and prone to human error. While we have seen attempts to automate this using traditional machine learning, this model often struggles when faced with complex, messy reality of agricultural environments, things like varying lighting, shadows, and crop density. This brings us to the core problem we are solving. First, environmental variability. Real world images change drastically based on weather and time of day. Classical models often fail to generalize across these conditions without massive data sets. Second, scalability. Deep learning models like ResNet 50 are computationally heavy. They aren't always suitable for the kind of real time edge based processing you would need a drone flying over a field. A literature survey conducted through various conferences and journals helped us to understand where the technology currently stands. On one side, we have classical CNNs. Study shows that they improve accuracy but struggle with variability I just mentioned now. On the other side, we have quantum machine learning. Research suggests it is an excellent at learning patterns from small data sets. However, we identified a gap. No existing study has successfully combined a lightweight feature extractor like MobileNet V2 with a variational quantum classifier, especially for wheat harvesting. This is uncharted territory we explore. So the main issues in the classical ML algorithms are high intra-class variability. So basically, when there are two images and it's very minute changes between both images, it is very difficult to recognize the difference between both images. And lower class separability, limited generalization to a new field condition. This all key points also creates error and downsize the precision of machine learning models. Now, QML has already been starting to apply to the yield prediction, crop classification, soil analysis, and precision irrigation. Our research shows QML performs particularly well when training data is limited and the feature space is high dimensional or complex. Now, no existing agriculture system combines lightweight CNN feature extraction with quantum variational circuits VQC for final classification. Now, this particular system is offered because to create a better generalization with fewer training samples, reduced parameter count, NIST compatible circuit depth, high accuracy for small or imbalanced agricultural dataset. Therefore, a mobile net V2 PQC hybrid classifier directly addresses the limitation of both traditional CNN and standalone QML. A problem statement is basically when a wheat farmer generally recognizes the stage of harvest, it may be late, and 20 to 30% of crops can be ruined at the time they recognize that it's the time for harvest. To reduce this loss of crops and to predict on time, we are using the hybrid approach using QML. As this particular model also keep in mind for different conditions, new field conditions, variability, etc. So this model works over the aerial imagery taken from the satellite, and we have integrated MobileNet V2 for classical feature extraction with VQC. In currently VQC circuit, we have simulated over three configurations, that is 2 qubits, 4 qubits, and 6 qubits. and we have compared all the performances against the classical baselines. Now, the proposed HQCNN, which is Hybrid Quantum Classic Neural Network, combines MobileNet V2 for classical feature extraction with variational quantum circuit. When the input images are processed through a frozen MobileNet V2 to generate a 1280 dimensional feature vector. A linear reduction layer compresses this high-dimensional feature vector to match the number of qubits. The reduced features are transformed into the quantum rotation angle using a bounded mapping and using Pauli operators. These angles are encoded into a quantum circuit using R rotation gates, preparing the quantum state for variational processing. The VQC applies to shallow variational layers consisting of parameterized rotations and a C-note ladder entanglement pattern, enabling expressive quantum feature transformation while remaining less compatible. Quantum measurements are taken using Pauli-Z expectations values to obtain a compact quantum feature vector. Classical ReLU projection layer maps quantum outputs to 64 dimensions, followed by a sigmoid classifier that produces the final harvest or pre-harvest. The hybrid design exploits strong classical visual priors and quantum circuits expressivity, achieving high accuracy with low computational overhead. This is the system architecture. So when we input the data of a field, the sources can be UAV, drones, satellite-based imagery, anything. And in our particular data set, this is a custom data set which we have gathered. There are 3,543 images in this data set, and those data sets actually are combined from multiple classes such as antithesis, booting, tillering, heading, milking, and harvest. And after the model predicts, it will classify into two categories: harvest and pre-harvest stage, and multi-harvest. So when data is processed, the resizing of data is done, the image is done, and the normalization done based upon our data set. Now, it will be passed through MobileNet V2 to extract spatial features. Pre-trained model will give us the output feature dimension 1280, and then we'll pass it to our QCNN, where we have implemented the QNN through PyTorch and PennyLane library, which is used for basically quantum machine learning. So it helps us in qubit encoding, angle coding of classical features. So after this, when the processed image will pass on to an hybrid layer integration, and finally we will get our output as a probability that whether it is in harvest or pre-harvest or not harvest. Now, as I mentioned earlier, we have 3,558 images, and we have split it up into 70% for training, 50% for validation, and 15% for testing. And we are also doing the imbalance handling, because if we don't, it will always give the probability towards the more images present in the data set. The main challenges that we find while creating a data set were gathering the images, because there is not such an authentic data or one place where all the images of agriculture with the label are there. So this was one challenge that we overcame while making this HQCNN. So let's talk about the results. As you can see now, we have tested on three configurations: 2, 4, and 6 qubits. As you can see on the screen, while the quantum classical ResNet 50 achieved 86.86% accuracy, a 4 qubit hybrid model achieved an incredible 99.88% accuracy. Even more importantly, look at the precision and F1 score, which are both 0.98. This is critical because in farming, a false positive means cutting the crop too early, which destroys value. Our model efficiently eliminates that risk. Conclusion: To conclude, we have successfully developed a hybrid model that outperforms heavy classical baseline while remaining computationally efficient. Taking just 225 milliseconds per image, we found that 4 qubits was sweet spot for this task. Offering the perfect balance of accuracy and speed for future work, we aim to deploy this real quantum hardware and expand the classification to detect multiple growth stages, not just final harvest integration. Thank you for your time.